Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today, we're working out of Elementary Principles of Chemical Processes 3rd edition, and we're doing problem number 4.7. Liquid extraction is an operation used to separate the components of a liquid mixture of two or more species. In the simplest case, the mixture contains two components, a solute and a liquid solvent. The mixture is contacted in an agitated vessel and a second liquid solvent, C, that has two key properties. A dissolves into it, and B is immiscible or nearly immiscible with it. For example, B may be water, C a hydrocarbon oil, and A species that dissolves in both water and oil. Some of the A transfers from B to C, and then the B-rich, the raffinate, and the C-rich phase, the extract, separate from each other in a settling tank. If the raffinate is then contacted with fresh C in another stage, more A will be transferred from it. This process can be repeated until essentially all of the A has been extracted from B. Shown below in a flowchart of a process in which acetic acid, A, is extracted from a mixture of acetic acid and water, B, into 1-hexanol, C, a liquid immiscible with water. And then they give a diagram here. I drew this diagram because it kind of helps explain what they're talking about here. So you've got this mixture here. It has B and a little bit of A mixed into it, and then you mix it with C. And there's this barren phase where C doesn't have any A in it, and then you mix the C with this feedstock, and then out comes C with A, and then this B phase has less A in it because it pulled it out. And they use this method a lot. So this method is used in this example. It's used to extract acetic acid out of water. And when I worked at a copper mine, they used a similar process where they had a hydrocarbon that had an element in it that would extract copper out of a water solution as well in order to help concentrate and purify it. So this process is used all over the place. This is the diagram that they give to us in the book. Part A, what is the maximum number of independent material balances that can be written for this process? Okay, so maximum number of material balances. Here's the rule. Material balance rule. If there's no reaction, and there is not a reaction in this case, this is a separations process, not a reactor, must equal the number of species. In this case, number of species is 3. Okay, so if you're doing a material balance, the rule is that you can only do a number of material balances equal to the number of species. And in this case, we have A, B, and C. So the number of species is 3. All right, part B, calculate MC, ME, and MR using the given mixture feed rate as a basis and writing balances in an order such that you never have an equation that involves more than one unknown variable. Okay, so that's a fancy way of saying use the substitution method in order to solve a system of equations. Okay, so let's start doing our substitution method. Let's start with the B phase. So we'll do our balance around the B phase. There's no generation, there's no accumulation, there's no consumption, there's no reaction going on. So it's just in minus out, okay? In minus out, so there's no B in phase 1, or in stream 1, there's B in stream 2 and stream 3, and there's no B in stream 4. Okay, so it's just stream 2 equals stream 3. Whatever goes in stream 2 has to come out stream 3. And then you solve for what M3 is because all of these things are known. Okay? and you get this. And that's MR. That's the flow rate of the raffinate. All right, let's do another material balance around C. Very similar setup. And we get in minus out, but there's too many unknowns here, so we can't do a substitution yet. But we'll just kind of leave it at that and then do our last material balance. So we can either do a material balance around the total, or we can do a material balance around A. And when I looked at it, I said, total looks easier, so I'll just do the total. Remember, we can only do 3 independent material balances. And look, I have 4. It looks like I have 4. B, C, and total or A, right? That's why I put or here, okay? Because total, if we use B and C, total is not independent of A. Okay, so you don't actually have 4 here. You can choose which one you want to use, either total or A, and then you'll have 3 independent equations. If I use all 4 of them, I won't have an independent set of equations. Okay. Okay, so this is my in minus out basically here. So I have streams going in and I have streams going out. That's my total balance. Well, then I can just substitute in whatever M1 is with these from this equation back into this, and then maybe we'll solve for something that we don't know. In the problem setup, I realized that the concentration of stream 1 is pure organic phase. So that is equal to 1. So right here I wrote assume that equals 1, and then I reread the problem and I realized, oh yeah, that's a good assumption. They actually set up the problem in this way. Otherwise we don't have enough information to solve the problem. Okay. So we just basically do the algebra from here. After we do this substitution, we do some simplifications and we solve for M4. And all of these things are known, especially if we assume that equals 1, and then we solve. Okay, the mass flow rate of the extract is 461. And now that we know what M4 is, we can go back to our initial total balance, and we have each one of those components now. And so now we just solve for M1, which is the mass flow rate of component C. Part C. Calculate the difference between the amount of acetic acid in the feed mixture and that in the 0.5% mixture, and show that it equals the amount that leaves in the 9.6% mixture. So basically we're just doing this mass balance. We say, okay, we said that these components are equal to this, and that these components are equal to this. Just prove that they are actually equal to each other. Whatever goes in comes out. We're basically just doing like a math check here to see if our math has worked out. And yes, they do work out. Okay. Part D. Acetic acid is relatively difficult to separate completely from water by distillation, and relatively easy to separate from hexanol by distillation. Sketch a flowchart of a 2-unit process that might be used to recover nearly pure acetic acid from an acetic acid water mixture. Okay, so I've got my feed in here that's a water acid mixture. It goes into an extractor unit like we showed above. And this extractor series extracts the acid from the water and puts it into the hexanol. Okay. So then the hexanol, the raffinate, goes over to this distillation column, and then the distillation column separates the acid from the distillate, which is the hexanol. And then the hexanol, the pure hexanol, goes back into the extraction unit. So just the raffinate just kind of circles around like this. And if I drew a big box around this thing, we would have water and acid going in, and we would have water coming out and acid coming out. total separation in that way. That is it for problem number 4.7. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.